Welcome to The Explainer. Today, we're tackling a really powerful idea, one that shapes everything from medical tests all the way to artificial intelligence. I'm talking about Bayes' formula. It's a fundamental tool for thinking rationally, and by the end of this, you're really going to see why.
So let's just dive right in with a medical puzzle that seriously messes with our intuition. It's a classic example for a reason. It shows just how tricky our brains can be when it comes to probability.
Okay, take a second to really think about that. You've got this test that's 95% accurate at catching the disease and 99% accurate at clearing healthy people. So you test positive. Your first gut reaction is probably that you're somewhere around 95% likely to be sick, right? I mean, it just seems logical.
But get this, the actual probability is just over 32%. I know, right? That is shocking for most people. It creates this huge gap between what we expect and what's real. And it just begs the question, why is our intuition so wrong here? What critical piece of information are we missing?
Well, the answer lies in a formal system, a way of updating our beliefs when we get new evidence. It's a method for moving from an initial guess to a much more refined, accurate conclusion. And that system is called Bayes' theorem. Now, I know the formula itself can look a little intimidating, all these letters and brackets, but the logic behind it is actually beautifully simple. It's really just about connecting what we want to know, like the probability of a cause given some effect, with the information we actually have. Let's break it down. So here's the crucial point. You don't just look at the evidence in a vacuum. You always start with what's called a prior belief. In our medical case, that's the fact that the disease is extremely rare. That's your starting point. Then you take the new evidence, the positive test result, and you use it to update that prior belief. What you end up with is a new, more informed posterior belief. You know, there's actually an even more intuitive way to think about this, called the odds form. Instead of dealing with complex fractions, you just think of it as simple multiplication. You have your initial odds, and the new evidence just multiplies those odds to scale them up or down. That's it. It gives you your new updated odds.
All right, let's move on to a couple of real-world examples to see how this works and really build our understanding. We'll start with a classic detective problem.
Okay, imagine a detective. Based on all the preliminary information she has, she's about 60% certain that a particular suspect is guilty. It's a good lead, but it's not a slam dunk. And then, a new piece of forensic evidence comes to light. This new piece of evidence is a specific characteristic. We know the guilty person has this trait, 100%. But it's not totally unique. About 20% of the innocent population also shares this trait. So how much should this new information really change the inspector's confidence? Well, after you run the numbers through the formula, the inspector's certainty jumps from 60% all the way to over 88%. And this just brilliantly illustrates the power of the theorem. A single piece of evidence can dramatically and, more importantly, quantifiably strengthen the case. Okay, now for a much more surprising result. This one's about quality control in a factory, and it really highlights the importance of that prior belief, that starting point we talked about. So, a factory makes 3 types of flashlights. Type 1 is the best quality, but it's also the rarest. Type 3 is the lowest quality, but it makes up half of the factory's entire stock. Now let's say you just grab one at random. And here's the big twist. If that random flashlight you picked works perfectly for over 100 hours, which type is it most likely to be? Our intuition screams type 1, right? The best quality one. But Bayes' theorem tells us it's most likely to be type 3, the worst one. So why? It's simply because there are so many of them. The sheer volume of type 3s means that in total, they produce more long-lasting units, even though their individual success rate is way lower. So why do we get these things wrong so often? It usually comes down to a very common logical mistake, something called the base rate fallacy. It's where we get so focused on the new evidence that we totally ignore the starting probabilities.
This exact fallacy was at the heart of a famous cheating scandal at the World Bridge Championships. The prosecution's case was basically this. The defendant's unusual playing style was consistent with them cheated.
But as Bayes' theorem shows us, that's only half the story. The evidence only really matters if it's more likely to happen if they're guilty than if they're innocent. I mean, if their strange play could also just be explained by them being brilliant, unconventional players, then the evidence isn't very strong at all, is it? And this way of thinking, it's not just for solving brain teasers we're looking at old scandals. It is the engine of rational thinking whenever we're facing uncertainty.
Bayes' theorem is the mathematical foundation for how we rationally update our beliefs. And it's running behind the scenes in countless fields that shape our world, from the spam filter in your email to how a doctor makes a diagnosis, all the way to the development of artificial intelligence. So, the crucial takeaway here is this. Bayes isn't just a formula. It's a mindset. It's a structured way to think critically about the world, to weigh evidence properly, and to be willing to update our beliefs. Which leaves us with a final thought to ponder. What belief do you hold that the right piece of evidence could completely flip on its head?